Okay, apologies for not recording from the start. So just one more whistle stop tour of what we're going to cover today. Um, we're going to cover gravity and artificial gravity. And it's kind of look picture of Newton under a tree. And we have this is an image correct as of yesterday of all the satellites in Earth orbit. So kind of the green ones are tiny little satellites about the size of a small car. Um, and the red ones, which you kind of can see, there's like one there, are satellites the size of kind of buses, like a large bus. And I think it's incredible just how many satellites there are. And this, I kind of won't go into this, but this creates a whole host of problems when it comes to imaging the universe. If you have a telescope on Earth, and there's kind of thousands of satellites in low Earth orbit, they're going to keep kind of flying through your image as you image the universe. So there's a kind of debate amongst astronomers and um, kind of companies where they want to keep sending satellites up into space, and astronomers are kind of saying you need to stop because we've spent tens, hundreds of millions of pounds on telescopes to put in kind of Chile and Hawaii and etc. And we can't even really use them because you've got satellites in the way. Um, ah, so the kind of different satellites um, will be uh, it kind of is less so their function doesn't depend on their size. Their size is more a matter of how advanced the satellite's technology is. The more advanced it is, the smaller they can make it. And it's also a matter of how much that satellite is trying to do at once. So the majority of these satellites are going to be communication satellites and GPS satellites. Um, so if you have a kind of sat nav on your phone, or potentially that could be using telecoms towers, but it could also be using GPS. So these satellites, the big red ones versus the kind of smaller green ones, will really just be depending on the company how big they're able to or how small they're able to make their satellite technology. It's not really a function of like the red ones are military satellites and the kind of the smaller ones are kind of civilian stuff. The Something you might be familiar with is Starlink. You might have heard about this in the news recently. It's kind of SpaceX's Wi-Fi communication satellites, and I think I might well be mistaken, but I think these lines might well be the Starlink satellites. Could be wrong though. Could well be wrong. Yeah, there is totally the possibility these satellites can collide in space. It it at the moment is under control. These satellites cost tens, if not hundreds of millions of pounds to put in space. So if companies were just sending them into space and they were just crashing into each other all the time, um, they probably would stop. But yeah, there is a real risk that they run into space because you can put a satellite up into space and you can control the orbit you think it's going to have based on the trajectory of its launch. But once it's in space, they don't carry enough fuel to be able to maneuver them. If you start here orbiting Earth like this, they don't have enough fuel to kind of somehow change the orbit so that it's now going like this. So they have to be really careful. And one solution is you can see how there's a much thicker line close to Earth, and you can see there's less kind of, pardon me, they start to kind of merge in with the stars further out. So one solution would be to kind of put your satellite in low Earth orbit, but in a slightly higher low Earth orbit. Um, but yeah, it's a very real problem, and I actually don't know how they kind of manage it. I don't know whether it's a really big part of satellites or whether actually it's quite easy to kind of negate, but it's a very real problem. Then we talked about gravity. We talked about the equations that govern gravity, some of its properties, the fact it's kind of an attractive force, which means you may often have a kind of negative sign in front to kind of show that it's an attractive force, and it's propagated by mass. So it's a force caused by mass, and it's propagated by gluons, which by gravitons, which are kind of its subatomic kind of force carrier. And yeah, here are our equations that govern it. I think you have already seen these, so we won't dwell on them too long. We then talked about what is artificial gravity. And the answer is that artificial gravity isn't actually gravity at all. The artificial gravity that you kind of talk about in science fiction and stuff is actually something called the centrifugal force. And the centrifugal force is a outward facing force. You know, if we look at this image here, it's pointing like this, like that, like that. And it's a force that acts on rotating bodies. It's proportional to the speed of rotation. This omega is the angular velocity, or kind of, you can think about it as the speed of rotation, how many radians it's turning per second. So yeah, the way these work is this would spin probably relatively quite quickly, and it would exert a force downwards. And in theory, with a big enough rotating disk, you could have a kind of a city in space spinning around with kind of normal gravity. This is a centrifuge, and this is where you kind of it's the most common use of the centrifugal force. It's kind of maybe implied by how similar the names are, centrifuge and centrifugal force. These are used for separating chemicals or minerals based on their density. And it can also be used for separating blood. When you want to give a blood transplant, they take the blood, they whack it in a test tube here, they spin it around in a centrifuge so that all of this, these black dots you can imagine are red blood cells. And so all the red blood cells kind of gather at the bottom because they're heavier than the plasma, the kind of fluid that your red blood cells sit in, it's kind of actually like a yellowy color. And what they do is they skim off the red blood cells and a bit of the plasma, and that's what they inject into people that's what they kind of drip into people with blood transfusions. They want as kind of as pure blood as possible, and the red blood cells and the white blood cells are kind of the most important bit of blood. So yeah, when they do blood transplants, they spin it around and they kind of take the bit they really want. What I mean here by pseudo force is that in a non-inertial reference frame, this force doesn't actually exist. So if you were to spin around at the same speed as the object, you would see no reason why a force should be exerted on, in this case, the red blood cells. But it will be exerted because everything else is accelerating circularly. And it's just that the force on these objects that are spinning isn't the same as those around it. And it can give the impression of, we'll talk about this later, but it can give the impression of kind of weightlessness if kind of an object moves really quick and you're not experiencing the same force. So yeah, and then this is our a G-force simulator. So fighter pilots and stuff like that, and astronauts use these to simulate the acceleration forces that they would experience on their body when they kind of perform maneuvers in their fighter aircraft or in their kind of takeoff for rocket launchers. Where we've got to now is I've asked everybody to do this question, where you have to imagine you were kind of designing a spaceship or kind of a space station, and I want you to create a centrifugal force such that people on board feel this force just as gravity at a strength of 9.81 meters per second squared. So how fast would an artificial space station of diameter 100 meters have to spin in order to replicate this force? And what I haven't put on here is just the kind of magnitude of G, which is 6.67 times 10 to the negative 11. If you guys want to give that a go now and send me a message in the chat or unmute yourself, and I'll give you some hints. I'll try and kind of help us all get there. With the mass, we can do some algebra, and we can actually make it so that we don't need the mass. If you, yeah. So yeah, if you're trying to sub masses in, maybe have another think. We don't actually need to. Let me, Kinza, let me do some maths on my calculator. I've got mine in angular velocity, but I will check to see if your linear velocity is correct. 2 seconds. Yeah, that's spot on. Well done. Just give everybody another couple of minutes. And if anybody would like any hints as to how we might start, please let me know. Or if you don't know what equations to use, let me know. I've got some hints lined up for you. Yeah. Okay. So a small hint is these are the equations you might want. Yes, yeah, that's exactly right. That is the angular velocity. Yeah. Oh, a small correction to that. Angular velocity. Think about your units. Um, you've given units of acceleration. Think again about what the units might be. How are people getting on? Would you like another small hint, or um, Kinza? The units are going to be radians per second, because yeah, exactly. Well done. Yeah, because we're looking at rotation. So for a linear velocity, a normal velocity, you're exactly right. It would be meters per second. But here we're talking about rotation, so it's going to be radians per second. Um, so we won't need a mass. If we do some smart algebra, we can get rid of the masses. They can cancel each other out. Yeah, no worries, no worries. We'll go through it in a minute. Are people happy if I go through it, or if I a kind of the final hint would be that what we really want to do, we're talking about matching the acceleration, or the kind of this is just acceleration due to gravity. As opposed to thinking about acceleration, maybe think about force. What we're trying to do is make the force exerted on people on these kind of spacecraft equal to the force they would experience on Earth. So mathematically, how do we express that we want to make this force equal to the centrifugal force? I'll give you 30 seconds and then I'll go through the answer. Okay, I'm about to stick the answers up. If anybody is still going and really, really doesn't want to see the answers, um, let me know now. Otherwise, I'm gonna spoil it all. Okay, answers time. So what we do is we want the force experienced on both bodies to be the same. So if we know these are our two forces, we can say that we want the force due to the centrifugal force to be equal to the force due to gravity, and we can set them equal to one another. If we say that Fc is equal to Fg, and we're just equating these two expressions, and this is what I was saying about the mass. If we equate these two expressions, they're both going to have mass, and this mass here is going to be the mass of the object or the mass of the person. But for the sake of this, you don't need to know it because they're going to cancel out. So when they cancel, we're left with omega squared is equal to g, which is our 9.81 over radius. Importance of radius rather than diameter. I've been a bit sneaky and given you the diameter. So we need to turn diameter into radius and then kind of square root both sides. And once we sub the numbers in, we'll get omega is equal to the square root of 9.81 over half of the diameter, so 50, which is equal to 0.44 rads. And equally, you could have worked out linear velocity by using the equation up here. But yeah, the question was asking for angular velocity. So there we go. That's how it works. Does that make sense to anybody that wasn't quite sure? Is there anything you'd like me to discuss or kind of explain again?
Sir, I have a question.
Yeah, by the way.
What does these two symbols FC and FG represent?
So FC represents the force on the body due to the centrifugal force. And FG is the force due to gravity. So F is just force, and I've put the subscript there so that we know which force we're talking about. Is that okay?
But sir, I'm still confused. How can we put these two forces equal to each other?
So the reason we can do it is because we are when you stand on Earth, gravity exerts a force on you, right? The gravitational field strength of the Earth, G, is equal to 9.81, and that exerts a force on you, which is proportional to your mass times that acceleration. What the question is asking in kind of fundamental terms is it's asking how fast would this spacecraft have to spin for the force exerted on you on the spacecraft to be the same as the force exerted on you when you're stood on Earth, because we want you to feel the same. So we need the force from the spacecraft to be equal to the force of gravity, right? And if we're saying that the force on the spacecraft is due to this centrifugal force here, and we need that to be equal to the gravitational force for you to kind of experience the same acceleration, or that same kind of force of gravity, then what we'll do is we'll set the two equal to one another, and that allows us to drop the mass. It's kind of less of a mathematical justification and more of a kind of conceptual, that's why the forces must be equal. Might not like it, but does it kind of make sense?
So I have another question.
Yeah, go on.
Are centrifugal and centripetal forces action-reaction forces?
Yes, they are indeed. Yeah. So the centrifugal force is the force that points outwards, and it kind of pulls things away from the center of rotation. And the centripetal force is the force that stops something just flying off of its orbit. If we go back to this, for example, if we had no centripetal force, as this spins, you just have a linear velocity and it would just fly off into space. The centripetal force is what pulls it back in to keep it in circular motion. Is a centripetal and gravitational force equal? For this case, for this question, the centripetal and gravitational force would be equal and opposite. Obviously, in the spinning body, there's not going to be any gravitational force because that's only when we're on Earth. But when we're saying that we're rotating and that rotationary centrifugal force is equal to gravity, then the reaction centripetal force must be equal in magnitude but opposite in direction. Yeah. Is the centrifugal force an imaginary force? Yes, it is. It's a pseudo force, much like the centrifugal force. They pseudo force. It might. I'm not sure. Hold on, give me 1 second. Let me check my notes. It might not be actually. No, sorry, I'm wrong. The centripetal force is an imaginary force as well, yes, because there's no fundamental physics for it. You know, there's no mass that's kind of creating a gravitational force, or there's no um, magnetic field creating a magnetic force, or kind of electric field creating an electric force. Happy? Are you okay if I move on? The next bit I have for you is I think is our kind of cool. We've got a couple of cool videos to show you. So if everybody's happy, lovely. Okay, cool. Right. So talked about it just briefly, but G-force. We had those G-force simulators that use the centrifugal force to kind of model the forces that pilots might feel when they pull maneuvers like this, where they're kind of flying and they turn very rapidly, or astronauts might feel when they take off. Um, G-force is just a measure of acceleration, and we measure G's in terms of 1G, 2G's, 5G's, 10G's, and what that means is just take the gravitational constant, take the gravitational force to be equal to 10 meters per second squared as a rough estimate. Then 5G's just means you're accelerating at a rate of 50 meters per second squared, or 10G's is going to be 100 meters per second squared. And we often talk about G-force as a way of measuring the stress either on the human body, because if you accelerate too much, you might damage people's internal organs, their brains, human beings are quite delicate in some ways. And we also measure it as a stress that objects can take. The wings on a fighter jet might be rated to 10 Gs. And if that fighter jet pulls more than 10 Gs, then the wings may bend, or parts of the aircraft may break because they can't take that force. So what I have for you now is a little, 1 second, I'm just trying to get these videos up in the background, and then I'll flip the screen over. Right. So resume share. Oh, no. Here we go. So you should now be able to see Safari. Can everyone see this? The guy in the chair,
Yes,
hopefully.
sir.
Cool. So look, this is what happens to the human body as they experience more force. So 9Gs, the amount of force he's experiencing here, would be equal to kind of probably the maximum force that a fighter pilot might experience if they made a really, really sharp turn. And if you can see, he's doing this kind of like he's taking a breath and then kind of straining really hard and taking another breath. This is a method used by fighter pilots and astronauts when they're pulling Gs, to keep all the blood in their kind of in their core, and stop it all just flowing down to their legs and then losing consciousness. Because if your blood all flows down to your legs, then your brain will kind of temporarily switch off. And it's not. There's been quite a lot of research done into it, and they think that kind of in the short term, if you lost consciousness, it's not particularly dangerous. But I've got a little video for you now. Can you hear him talking there? I've got a kind of couple minutes of the video to play you, and hopefully, uh, find this interesting. I think this is quite fascinating. So this is Oh, you can't hear it. If I play, can you hear that or no?
No, sir.
Oh, you can't hear that. Oh, that is so annoying. Um, oh, why is that? Right. In which case, the subtitles are on at the bottom. So read along with the subtitles, and I will try and talk you through. I will try and talk you through what's happening. So here's a video of during the kind of Cold War era, so 1969, the Americans used rocket sleds to test the impact of G-force on the human body because they had no idea what it meant. And this was kind of mid space race. And so here you can see a clip of a man basically strapped to a rocket flying through the desert. And they did this because they had no idea what the impact of G-force was on the human body. And positive G-force is going to kind of compress you into your seat, much like the clip we just saw of that man there before. But a negative G-force is essentially just if you were driving a car and you hit a wall. It's just a rapid deceleration. What we'll see, I'll skip some of this then because he's talking about all this stuff. So what he's doing now is what fighter pilots do in order to train for the kind of forces that their body will experience during flight. And here you can see the forces that he is experiencing. So 1G is just normal, what you or I experience whilst we're sat here right now. And jerk is the rate of change of G. So it's the acceleration of G force, the increase of G force. 2G, his body is going to feel twice as heavy as it did before. I'll skip us forward a little bit more. So is it 1.5 Gs now? And now they're starting to increase it. And so you can start to see his kind of face change shape as there's forces acting on his cheeks and stuff that and then this is what happens if the human body is exposed to too much G-force. So he's doing the breathing method to try and stop himself going unconscious, and he's kind of lost consciousness there. It's kind of a bit horrible, but there's actually no significant impact to losing consciousness due to gravity. And look, he's kind of back talking now, and he's completely fine. And this is just her explaining that it's not dangerous. But if you were, well, what they're saying is it's not dangerous, but if you were flying an aircraft and you lost consciousness, that obviously is very dangerous. Go back to that now. That's annoying. You can hear that. That kind of, it's a cool video. I might send the link and you can watch that if you fancy in your own time. The final thing I have to show you today then is kind of asked about gravity-free systems. And again, kind of in a simple explanation, there is no such thing as a gravity-free system. Gravity is a force that goes on for infinity. You know, it will reach infinitely far. We define the potential due to gravity as being zero. In other words, the force people experience due to gravity is be zero when somebody is infinitely far away from a mass. So because it's impossible to get infinitely far away, in theory, it's impossible to have a proper gravity-free system. But in practice, we can have essentially gravity-free essentially gravity-free systems. And those systems we call microgravity. And that's what you see in spacecraft. When people are floating around, they are still experiencing some gravity, but very, very little. And other scenarios where you might see kind of gravity-free systems are if you take somebody being in a lift, when the lift is going upwards, they're going to be temporarily heavier because they're experiencing the force due to gravity and this acceleration force from the lift. So in this case, he's going to be kind of 1.5 times heavier. The converse is true when accelerating downwards. There'll be a brief period of time where he's kind of half as kind of heavy as he used to be. And if the lift were to just snap and you were to begin to free fall, everything in the lift would be accelerating down at the speed of gravity. And so it would mean that there'd be no resultant force between the man in the lift and the lift itself. And so he would feel weightless in kind of his environment. Now, in reality, he's not weightless. In reality, he's falling, and the weight he's experiencing is just in a kind of bigger picture. But in his kind of reference frame, in his view of the world, he's weightless because the lift is falling at the same speed as he is. So he's not experiencing any of this force. And an example of that is these kind of zero gravity planes. These planes fly up really, really high. And then what they do is they plummet at the kind of, it's almost as if they just switched off their engines. They just fall out the sky and nosedive towards the floor. And for the kind of 30 seconds, a minute that they're falling straight towards the floor, everything in the plane will feel weightless. And it's just a consequence of this kind of moving at the same speed as your reference frame. And if you've ever been on a roller coaster or sat in a car, when you go over a bump and you get that kind of weird feeling in your stomach, that's just kind of a brief moment of weightlessness, which is quite cool. And yeah, that's everything for today.
I want to
so
know.
if you've got any questions, fire away.
I want to know why
Otherwise,
does a
I'll
body.
I'll send that link to the group chat and you can watch that video. But otherwise, that's us for today. Any questions?
Sir, why does a body become weightless in free fall?
No. In which case, what I will do is I will stop the recording and I will send you guys a link to the recording so you can watch it same as last week. Apologies again for not starting the recording sooner. That's kind of my fault. And yeah, I will see you guys same time next week. Okay. Okay. Bye, guys. Oh, thank you very much. Good. I'm glad you enjoyed it.